Hi everyone. Hope you can hear me okay.
Yep.
Um, so I'm going to talk about my home lighting system. Let's just get that back to there. Um, right, let's just go back to that. Right, so this is a sort of home lighting system, and the idea was I wanted something that I could use in the loft and outside under the eaves. I actually live in a bungalow, so it's kind of, the eaves are quite close to the ground, and the idea was that I was going to have quite a few of these little lights up in the loft, probably about 10 of these or so, and then about 2 or 3 per wall outside. So probably about maybe 12 on that. So in total, probably about 20 of these little LED panels, these 2-watt LED panels. Let's just quickly go through about different types of lighting. So this picture here, we've got a candle on the left-hand side, and then the incandescent light bulb, which we used for pretty much all of the 20th century, and they're very inefficient. So 100-watt light, they're about 2% efficient. So 100-watt light bulb is going to be about 2 watts of light and about 98 watts of heat. And then the next bulb you've got there is a compact fluorescent bulb, which is 8% efficiency. And fluorescent bulbs aren't anything new, but the advance they had with the CFLs, was that they managed to get them into a standard light fitting. And then the next one along is LED lighting, and these tend to be 25% efficient, and I think theoretically they can get up to about 40% efficiency. So they're obviously the way to go to save the planet and stop using lots of electricity. Saw these on AliExpress. These are chip, COB stands for chip on board. These are little LED panels. They got about 15 LEDs on each panel. These are actually being advertised as suitable for replacing your interior light in a car. So they're very inexpensive, as you can see. And so I ordered some of these. And when I got them, I tried them out from 8 volts to 12 volts. And they work okay. They're not very bright at 8 volts, but they're very bright at 12, and they're okay at 10 volts. So interestingly, the car voltage is 14 volts, and I haven't actually tried them at 14 volts. So maybe I'll try that sort of another time, but I'm not sure they'll last that long if you run them at 14 volts, to be honest. They get very hot at 12 volts. I think I measured them at about 100 degrees C. One of the interesting things about these, because I thought these were just going to be white LEDs, but they're actually blue LEDs with a phosphor coating, and they convert the blue light to white light. I guess in a similar way to the compact fluorescent bulbs. And I think the reason for this is because the blue LEDs, as far as I know, are the most efficient LEDs that you can get. And I said that it's got 15 LEDs. There's 3 in series, and then there's five blocks of these. So there's 5 in parallel sets of 3, and it's got a series resistor to limit the current. But that cuts the efficiency down by 75%. So if they were 25% efficient, they're now 18% efficient, but that's still okay. So I needed a 12-volt supply to power these things. So again, I looked on AliExpress, and you can see they've got all sorts of different voltages, going from 5 volts all the way up to 90 volts, and the current goes from sort of 1 amp to 70 amps, which is a bit scary. I sort of was interested in the 12-volt 5 amp one and 12-volt 10 amp one, which were £6 and £10. So I got one of each of those. Now you could, you could just connect that up to those, and then that's it, job done. You've got your lighting. But I wanted something a bit more, a bit cleverer than that. So this was going to go through a controller board, and this was my kind of list of the things that I wanted to get out of the controller board. So I wanted it to work through Wi-Fi, so that I could do this through a smartphone or sort of something like Alexa or something like that. And I was going to use MOSFETs to turn the LEDs on and off, and also to control the brightness using PWM, pulse width modulation. And I wanted several different circuits. So rather than having sort of 30 of those little boards and they all come on at once, I wanted some to come on, and some, so I wanted sort of several circuits so I could do that. And obviously, this needs to be sort of fail safe and secure. My last talk was about security, so I thought it'd be a good idea to put some security into this thing, so that and not just anyone could just sort of hack into it. So that was the that's a kind of thrown together little picture that I did of how I saw this all working. The most important thing on here, I don't know if you can see my cursor, is the lights down at the bottom there, and those are connected up to the controller board, and that gets its power from this what they call a lighting transformer, which is actually a switch mode power supply, and that's connected to the mains. And I put this smart plug in there for safety, so as a last resort, if I spot that something's gone wrong, then I can just sort of pull the power to the lighting transformer, and it'll just sort of cut the power to the lights. The controller board has got is going to have a web API on it, but it's not going to have much sort of intelligence on it. So that's most of that is going to be done through the Raspberry Pi. So that talks to the controller board, and if you want to do things like turning the lights off when it gets dark and that sort of thing, that's what the Raspberry Pi is going to do. And this would also provide a web interface to things like I've got a smartphone here, so you could just sort of pull up a browser on there and have a web interface to it. So that brings me on to the software design, and this is the kind of basic architecture on here. So I've obviously got the controller board, which is a Wemos D1 Mini, so I'll come to that in a second, Raspberry Pi, and the client, which in this case is a smartphone. So on the Raspberry Pi, I was going to use Nginx and have a Vue.js web app on there, and that's obviously gets shown in the browser, and that talks to a Python web API, which talks to the web API on the controller board. Now, I could have gone directly from the web browser to the controller board, but it's kind of more secure this way, and there's sort of various reasons why I wanted to do it this way, and a couple of them, is the security, but also multicast DNS doesn't work on Android, so you'd have to use IP addresses rather than looking up the names. So that's kind of why I went for this architecture. So this was my first prototype. You can see that it's not connected to the LEDs or the 12-volt supply, just testing the Wi-Fi and the API. And I had a Wemos D1 Mini Pro in my box of bits. So that's an ESP8266 board. And so I thought I'd use that. There's plenty of Arduino examples that show you how to do web servers and doing the multicast DNS and various other things, the security and things like that. So I just modified some of those. And what I did was I created a web server with basic authentication, and because the password just gets sent straight across in plain text, then you have to do that on a secure connection. So that's what I did, and it's it's not quick. It takes about a second to do the request. But then that's because the ESP8266 does all the crypto stuff in software, as opposed to the ESP32 where it's done in hardware. So this was that kind of all worked okay. So then I went on to the next stage, which was prototype 2, and in this one I hooked up the 12-volt supply. I needed a way to drop the 12 volts to 5 volts for the WeMOS, and my first thought was to use a 7805 regulator. But I tried this and the regulator got hot, even though the D1 board was only using about 80 milliamps. So I decided to use a DC to DC converter, which is about 85% efficient, and that worked a lot better. You can see that just at the just in the middle there, and I had an N-channel MOSFET between the LED and ground, and that allowed me to switch the LED on and off, and also to do the brightness via PWM. And I just used the standard. The PWM is set to run at 1 kilohertz, so I just stuck with that because that did the job quite nicely. Now I realized that there was 12 volts on one side of the LEDs, even when the LEDs were off. And I thought this was okay until I accidentally shorted the 12-volt line to earth and discovered that the ground is connected to earth, and it started to melt the wire. I'm sure I think Tony's probably going to talk about that a bit later, isn't he? But so I decided it probably needed a bit more safety in there, and so I added a P-channel MOSFET to the 12-volt side. So you can see the two MOSFETs. There's I think that one there is the P-channel one, and that's the N-channel one. And I also decided to have a current sensing board to measure the current, and I modified that too, because normally, so I used an INA 219 board, and which will measure 3.2 amps, but I modified it. I put an extra bit of resistance on the shunt resistance so that I could measure 5.4 amps. So that was the circuit that I came up with, and I created this in LT Spice. I don't know, some of you will have heard of LT Spice. I mean, it's a very good sort of package. It's really used for simulating circuits, making sure they work. But I sort of know how to, I've used it quite a lot, so I quite like using it to draw the circuit diagram out as well. I had to create some other packages because it doesn't come with packages for the WeMOS board and things like its DC to DC converter. So I had to add these myself, and you can't actually simulate those. I mean, you can't simulate what a WeMOS D1 board does, but you can sort of include it in a circuit diagram like I have there. The N-channel MOSFETs, according to the data sheet, take a gate voltage between 2 volts and 4 volts, but I found that the ESP8266 output at 3.3 was enough to switch the MOSFET on. With hindsight, I could have used P-channel MOSFETs rather than the N-channel types, but the driver circuit, you can see, is a lot more, well, not a lot more, but it's a bit more complicated than the N-channel one, where you just drive it straight from the chip. And this way, I'm kind of happy with it. I think it allows me to switch both sides of the LED off. So I decided to put this onto Vero board, and this was the layout that I used. I did this in Paint.net, which is like Photoshop, and if you do it as multiple layers, then you can sort of move things around, sort of even now I could on this drawing here, it's sort of very sort of cluttered, but because it's different layers, I can move things around without sort of messing the whole diagram up. So that was the finished board, and there's nothing worse than plugging it in and something burning out. So I tested it first, especially with sort of 5 amps going through it potentially. So first thing I did was a visual check, and then I did a resistance check, and did find that some of the tracks were connected when they shouldn't be. So and the supply was actually connected to ground. So if I had just plugged it in, it would have something would have gone bang. So so I sort of fixed that before I actually plugged it in. And a couple of the WeMOS outputs were shorted to ground, so I fixed that. Then I went on to the next stage, and first thing I did was plug the WeMOS board into the PC first, and that all worked fine. So then I went on to putting the 12-volt supply on and checking that all the LEDs could be turned on and off. There's a wire missing on one of the MOSFETs, so I fixed that, and then it was all good to go. So after I did that, I then started to measure the voltage and currents at various points. This was the test results. This was my first set of test results. I actually did this on the prototype board, and the things that I was looking for were the current going through one LED panel was 120 milliamps, and actually with the input voltage was 12.1 volts, but the voltage across the LED panel was 10.3 volts, so it's quite a drop. But actually a lot of this was due to using the breadboard, and some of the wires that were connected up on the breadboard. So kind of the moral of this tale is that the breadboards aren't very good for this kind of high current application. I did manage to measure the voltage across the MOSFETs, which when they were on was around about 7 millivolts, and I calculated that was the on resistance of about 60 milliohms. Again, for one LED, there was 13 millivolts across the Iron A219 board, which is, what we'd expect. And, there's I've said there's 27 millivolts was accounted for, but there was actually a, 1800 millivolt loss. So, not great. And the on resistance is supposed to be 20 milliohms, and so I wasn't too happy with 60 milliohms. But actually, if you go to this link here, which I won't do now, but it does actually tell you about what to expect from that, and the fact that I was driving this at 3.3 volts is one of the things that made a difference. And there's kind of various other things that made a difference as well. When they sort of say that it has a 20 milliohm resistance, that's actually with 10 volts on the gate. So the P-channel MOSFET was the one that's going to take the most current, and I worked out that at 3 amps it was going to dissipate about half a watt, and at 5 amps it was going to dissipate 1.5 watts, and that was the temperatures that I calculated it would get up to. So I didn't really want to put heatsink on the MOSFETs, but I think with that temperature I was going to have to. So the second set of test results I did were on the Vero board, and on this one I had 6 LED panels, plus I had a 4.7 ohm resistor, because I didn't want to put sort of 30 LED panels on there because it would get too bright. It's these are incredible. Even having 6 of them is quite bright. But with that on there, the total current was 3.3 amps. So this was quite a good test of the board. And unlike the prototype board, this time I had 11.8 volts on the board, and then 11.3 volts across the LED panel. That's running at 3 amps, over 3 amps. And then the voltage across the 219 board had gone up to 200 millivolts. But again, you know, that's what I'd expect. The voltage across the P-channel Mosfet, I calculated, it gave me a resistance of 67 milliohms, which I measured as close as possible to the Mosfet. You know, as I say, I'm not entirely happy about that, but I'll come back to that later. The N-channel MOSFETs were between 31 milliohms and 34 milliohms, which you know, I'm quite happy with, and they actually ran quite cool. But the P-channel MOSFET did, as I calculated it, it did actually run a 58 degrees C at 3.3 amps. So I put a heatsink on there, and then that brought it down to about 38 degrees C. Now I noticed that the LEDs flash on when I powered up or reset. So I'm just going to see if I can bring up a video to show that. Right. I'm guessing you're still seeing the slides at the moment.
Yeah, just seeing the slides.
Okay, so I think it's that one there.
Yeah,
okay, so hopefully that's showing the video.
Yeah.
So when I plug the power in, you can on the left-hand side, you can see the LEDs sort of flash, and when I reset it, they're flashing as well. And the reason why it does this, I'll just run that again.
I was going to say, if you do it through the file, share a file option, because it's impossible to see something flashing, particularly because
okay. Okay, that's fine. I mean, that's if I stop it at the relevant place, you can see the LEDs light up there. And you know, this it was only kind of briefly when you power up, and when I go and press the button there, you can see they kind of flash. You know, the reason for that is because all the I/O pins are sort of bouncing all over the place when you power up or reset. So let me just go back to the slides. So hopefully that one. Not sure that's the right one actually. That's that one there, I think. Is that should hopefully be showing the
test results too.
Okay, good. Yeah, so I noticed that the light LEDs flash, so I wasn't too happy about that. I'll come back to that in a second about what I did about that. So this is the MOSFETs that I'm using, and this is really just to show that these things are rated at 55 volts and 49 amps, but the only way you're going to get that is if you do get this resistance 17.5 milliohms and 20 milliohms for the P-channel MOSFET. So I was getting 30 milliohms for the N-channel MOSFET. So, you know, I'm still not going to be able to do 49 amps, but, you know, I could do the 5 amps. But for the P-channel MOSFET, because I was getting 60 milliohms, you know, I can do the 5 amps, but, you know, not going to get anywhere near that. So I'm sort of running out of time out here, aren't I? I was going to show the LT splicing, but I don't think I'll do that. That I think is, you know, something for another day. Coming on to cable connectors. Now these were the things that I used. Surprise, surprise, I got these from AliExpress as well. These are spring-loaded connectors, And what you do with these is you lift the clip up, you put the wire in and then put the clip down. And I think that these are better than the terminal blocks because you don't have to sort of fiddle around with screws and it's less stress on the wire. There's lots of different types. So the ones I've got here are 1-to-1 and 1-to-3. And if you search for cable connector, then you'll find these things. And I've been very impressed with them. And wires. So there's sort of different bits of wire that you can use. I'm just going to do a little clip on a video for this one. Get rid of that one. Okay, this is a test to see how much current you can put through. Let me just stop that a second. I think it's that one. Just hopefully that's showing. This is a test to see how much current you can put through a piece of wire. The wire that I've chosen is this wire here, which is 30 gauge. So it's quite thin. There's probably about 300 meters of wire on here. So that would go quite a long way. I've connected up a 180 millimeters of wire between positive and negative, and I've got a temperature sensor in the middle, and I'm going to measure how much temperature rises with the increase in current. We'll start with 0.5 amp, and you can see that the on the left-hand side, we've got the voltage drop, which is 39.4 millivolts. And on the right, the temperature, which at the moment is 23 degrees C. So if we leave that for a little while, then we'll see what the temperature goes up to. Okay, so that hasn't really gone up very much. So let's increase the current to an amp and see how much the temperature goes up. Again, the temperature hasn't really increased that much. It has gone up a bit. You can see that the voltage drop across the wire is now over 80 millivolts, but nevertheless, the whole wire is only dissipating less than 1/10 of a watt. So we wouldn't expect the temperature to go up very much. So let's increase it to 2 amps now. And you can see the voltage across the wire has now gone up to 166 millivolts, and the temperature has started to increase. I mean, it's up to 30 degrees C now. So let's increase the current to 3 amps. Now, 274 millivolts across the wire, and the temperature has increased to 45 degrees. So this is up quite a lot on the 23 degrees ambient. So let's increase the current to 4 amps. And now you can see that the voltage drop has gone up to 0.4 of a volt, which is a significant amount of voltage for this short amount of wire. But the temperature has also increased to over 60 degrees. And finally, let's increase the current to 5 amps. The voltage drop across the wire is now well over 0.5 volt, and the temperature you can see is climbing quite quickly. And the temperature is now well over 90 degrees. This is way past the safe rating for this wire. Okay, so let me just go back to the slides. Presentation. Okay, so basically with wires, you get what you pay for. I'm sure Tony will tell me off for putting 5 amps through a piece of a wire wrap wire. It's really only rated at 0.5 amp, which I think is quite a sensible idea. If you do put more current than that through there, then you're going to get a big voltage drop anyway, so it's probably not going to be that useful. But this is the different bits of wire. 30 gauge wire, you can see has got quite a lot of resistance, 450 milliohms per meter. If you go to 24 gauge, which is this stuff in the middle here, then you've got, I actually measured this at 123 milliohms. Some people I think say it's about 80 milliohms per meter, and the current is maximum current for that is about 2 amps. That's about the same. Ribbon cable, I think, is, when I looked it up, was 24 gauge wire. So that's kind of the kind of thing that you can put through ribbon cable. And if you want to go for something that's going to take several amps, then you could go for something like this wire here, which is 10 gauge wire, and that's got a resistance of, supposedly, I haven't tried this out, but they claim that that's got a resistance of 4 milliohms per meter. But it get quite expensive if you wired all the LEDs up with that sort of wire everywhere. So I was going to use a combination of these different bits of wire. Now, one thing that you have to watch out for is you could actually, example I've used here is 30 gauge wire for 5 meters. It's got a 0.8 volt drop at 180 milliamps, so that's one LED. Now, that's acceptable, and you could do that. You could run that to one LED. But one thing that you have to be careful of is if you short that LED out, you might, just go back to that. If you short that LED out, you might kind of think that it'll blow a fuse or something, but it won't because of the resistance. So actually what will happen is if you short that piece of wire out, you'll get 2.6 amps going through the piece of wire, which as I've shown on that video, it's probably going to be okay, but it might not be. It might start a fire or something. So that is something that you do have to be careful of. Right, so I'm gonna try and go through this. I'm sort of taking quite a lot of time over this, but I'll just go through the software now. This, I did the software in the Arduino IDE. I could have used Platform IO and VS Code, but sometimes I think it's easier just to use the Arduino IDE, so that's what I did. This is an example of the code. This is just showing one of the routes. So you just have this thing, server on, that LED, and these brackets things, and that'll just do a web request and send back the I think this one's a put, so this is turning the LEDs on. There's lots of examples about how to do this in the Arduino code, and I just used one of those and modified it. One of the things that I've used a lot in the last few years is Swagger, and I think Swagger is fantastic. It's also called Open API now. It's been, I think that's it became a sort of standard probably about 3 or 4 years ago, and so it's also known as that. When I've used it in .NET and Python, you get it generates the definition for you automatically. Now you don't get this with the Wemos board, but what you can do is there's an editor. You can see the page I've gone to there, editor.swagger.io, and it allows you to edit the definition of the API, and you can actually, I'm not going to do that here, but you can actually generate server and client code. But what I'm going to do with this is I'm going to take this definition file and just load it into the Wemos board. So what you can do on any board, really, on any sort of server, is you can have this. This is the entire page for the Swagger user interface, and it's so small because it goes off and gets all the clever stuff from the CDNs. And so what you do is you serve this page, and then this page, when the window loads, it will say it's got down here window on load, and it requests a swagger.yaml file from the server. and that'll show the API on the screen. So in order to make this work, we just need to take that code there and this one here, and we just put that into the as a couple of strings on the Arduino code. And so that's what I've done here. And then what we do is when we get asked for the route, we send the Swagger UI page as HTML, and then that will then request the Swagger YAML file, and then we'll send that as well as a string. And when we do that, if you go to the navigate to that page, it'll come up with this, which is the API definition, and this allows you to see what all the different things that you can do are, and it allows you to test it as well. Okay, so this is the Raspberry Pi code, and what I did for this, all the code for this is all in one repository, one GitHub repository, but the bit that we're using here is for I've got two bits here. This Pi 3 is going to be the Python web API, and www is the Vue.js application. And I've created a workspace for this so that I can put some of the system files in there for Nginx. Now I installed Nginx is really easy to install on the Raspberry Pi. I'm not going to go through that because you can just kind of Google that, and it's really easy to set up. But this workspace gives me the folders here so that I can go in there and point Nginx at my web page. And I modified the architecture a bit. So I said earlier that I was going to have a web API in Python, and actually, because I was running out of time doing this, I decided to go directly from the browser to the WeMOS board. And the way that I did that was just by having a static IP address on the WeMOS board. Now, this does mean that it means that the authentication is done through basic authentication on the user has to do that. So, you know, what I really want to do is have something like a Google login, have what they call federated login. But on this first version, it's just basic authentication. So I'm kind of aware that I'm sort of getting close to the end of the time. So I'm sort of been rattling through these last ones. So that's kind of it for this version. I wonder if I can just demonstrate the bit I haven't shown you is the actual Vue application. So if I just do that, I don't know how to do that. I can find it on here. That one there. There we go. Right. So this is the web page on the Raspberry Pi. So RPi 8443. So this is an encrypted page. It says it's not secure because I'm using a self-signed certificate. And I've got two pages here, one for the brightness and where they're all set to full brightness at the moment, and one for turning these on and off. And I can click on those and you'll see that, I don't know if you can see it gets just got very bright in here. I can turn all these LEDs on. and it just gets extremely bright in here. So I'll turn all those off again. And that's all going through this. I mean, I can also go to the this is the Swagger API, so you can see it's going to WeMOS1 there, and I can do all the operations here. I can test them out, make sure that that these all work. And the nice thing about this is that you can sort of test out the back end, and then also you can do the front end and do the two things separately. Let's just go back and turn some of these off. For some reason, it says that one's still on when it isn't.
Can only see your screen, so can't see the LED going on.
Okay. Yeah, I mean, the only way you can see the LEDs going on and off is just to sort of see the whole sort of room light up where I am. But right, so I go back to the presentation.
We're running out of time. So anyone have any questions?
Yeah.
That was very interesting. Thank you. I was wondering if you'd considered using a PCB.
Yes, I have. I kind of thought that, you know, originally I kind of thought, yeah, I'll just stick with Vero board. But now, especially seeing as I'm thinking of doing another version of it, I am kind of thinking, well, you know, maybe I should do a PCB version. Given the sort of currents that are going around there, it might be an idea. I mean, I did notice with the Vero board there was quite, you know, there were some sort of voltage drops around some of it. Not as bad as breadboard, but you know, it's some of the tracks are quite close together, really. Which, as Tony talked about last month, you know, it's not great having some of these things so close together, especially when you're dealing with those sort of high sort of currents.
When you were measuring the currents and things like that, did you have any difficulty arising from them being pulse width modulated rather than constant?
So you're talking about when I was doing the pulse width modulated, you know, levels for the brightness.
Yes.
Yeah, I did that. Most of the testing I did with it was either I switched off completely or turned on completely. And to test the PWM out, I did actually hook it up to a scope to see what was going on. But that's obviously more complicated doing that. So that was just to kind of make sure that making sure that the MOSFETs were turning on and off quickly enough, for instance.
Thanks.
So what sort of improvements would you expect from a PCB then, if you're going to?
Well, I guess I could make the tracks thicker. They're quite thin on the Vero board. What I did do, I mean, I can't really show it at the moment, but what I did was I did sort of load the tracks up with lots of solder to where I knew there was lots of current that was going to go through it.
You mentioned about obviously Mosfet temperature is a thing you've got to keep an eye on. When driving with 3.3, I found to be safe, if you're doing the higher currents, that sometimes a MOSFET driver is not a bad idea, especially if you're using PWM. Then obviously you're going to spend some not insignificant time. I mean, 1 kilohertz is not so bad, but even then, with low current on the pin, you're going to spend some not insignificant time in that boundary region where there's actually a fairly significant distance on the MOSFET. and you'll probably see you could probably reduce the temperature on the MOSFET with the driver.
Yes. Yes, I know, I agree with that. Yeah. I'll just show the final slide actually, just so that that's the any question slide. But I've also got the GitHub page there as well. So everything's, I mean, including this presentation and all the LT Spice files and everything is in that GitHub repository. I mean, I don't know how many people have used LT Spice. It's I can only see a few people there, but you know, LT Spice is you know, I've been sort of very impressed with it. Having sort of done electronics for, well, decades now, you know, it certainly wasn't something that was available when I first started doing electronics, and you know, it hasn't, you know, to be honest, it hasn't really changed that much in the last few years, but it does simulate the circuits very well, I found.
So how happy are you with the actual lighting? Did the lighting actually meet your expectations?
Yes, I haven't actually installed it outside yet, because I think I probably will do. I'll just go back to that previous slide, but I think some of these things that I've got for version 2 of it, I need to do before I actually deploy this thing. So although I've got the current monitoring on there, it doesn't actually, you know, the idea was going to be that if I detected a short, then I would sort of cut the power to the lights, and I haven't actually got that at the moment. It monitors the current and it will tell me what the current is, but it won't actually cut the power. So I'd quite like to do that. I'd quite like to, I think I'd like to change to an ESP32 board, because I thought that it would be fine, you know, a second to turn the lights on. I thought that would be fine, but actually it is quite annoying having that delay. And the ESP32 board takes about 100 milliseconds rather than 1 second, so it's about 10 times faster. So I probably will do some of these changes before I actually deploy it.
Okay, thanks. So very good.
When you're saying create a tunnel for Alexa, and there's a lot of things on here, I'm wondering, maybe you might be in a better position if you use something like a home automation platform to run everything, rather than trying to integrate stuff yourself. One of the things that I've done is I've used the what's it called, Hue emulation feature to emulate Hue devices, which is natively understood by the Echo. So providing you're emulating that, and I did that through Home Assistant.
Yeah, no, that's a fair point. Yeah, I did. I mean, Home Assistant isn't something that I'm very familiar with, but it's certainly something that I was thinking about using. The other thing I was thinking of using was Node-RED, which I have used. I don't know. I quite like doing things the hard way and doing, you know, sort of doing it myself rather than using something, you know. But I must admit, it is reinventing the wheel a bit. Yeah, some of it.
Yeah, the plus side of the Hue emulation is that you don't have to worry about any cloud service sitting in between. Pretty much anything else you do with an Echo requires you to create a skill, which then is internet hosted and gets called via their service.
Yeah.
It doesn't solve the problem if the internet goes down, but it means you don't have to worry about hosting a service that's just going to run in your own house.
Yeah. Yeah, I mean, I think you know, this is you know, what I've got here so far is, well, it's not really finished actually, to be honest. But I kind of agree with Richard that it's what we all really want to know is the process of how I got there and the problems that I had, rather than just sort of seeing a sort of shiny finished example, because that's not really sort of kind of teaching anyone, you know, anything, or sort of showing, you know, it's better to sort of see the problems that I ran into rather than sort of me just sort of going, yeah, there we go, it all works perfectly.
Yep.
Gary, you have a question?
Yeah, quick one. Thanks for that, John. That was really, really informative to see your journey. I really enjoyed that story. So just a quick one. I mean, what are you going to do about casing and stuff like that? Because I know you're having loads of fun building it. Right?
Yeah.
Great. But you know, there is a practical application for that. I was just wondering, sort of, what your plans were around putting casings around it and keeping it safe and dry.
Yes, that's a good question. I'm not sure I'd really thought about it, to be honest, because actually this is going to be up in the loft, and the only person that goes up in the loft is me, and so I was kind of thinking I'll just leave it lying around up there.
Well, yeah, okay, fair enough. But I just want to also sort of offer an extension of a bit of help, because I've been messing with your ESP32s for a couple of years now. So if you get stuck, give us a shout. I'll be quite happy to help.
Okay, lovely, thank you.
Not that you'll need it, because you seem perfectly capable, but just in case, you know.
I did try the software is you know, there's examples for the ESP32 as well as the 8266, and I did actually try one of those out, and that's how I know that it's about 10 times quicker, because I did a web server on the ESP32 and it took about 100 milliseconds round trip. So
yeah, they're pretty cool. They're pretty cool.
You talked about the COBs getting hot. Would you consider putting heat sinks behind them?
Well, I do wonder whether you ought to put heat sinks behind them, yeah, because they do get quite hot. One of the things that doesn't help with those little panels is that they come with a little sticky back plastic on the back of them, but it's probably about 1 millimeter thick, that thing, and it's not made of thermal material, so it actually insulates the thing from anything that you stick it onto. So if I was going to put it on a heatsink, it'd probably be a good idea to sort of scrape all that sticky stuff off before I did that.
Yeah, cheers.
But yeah, 100 degrees C is a bit too hot, really. I mean, any kind of semiconductors that running at 100 degrees C aren't going to last too long, as far as I'm concerned.
It would certainly help with drying them out on a wet day.
Yeah. Yeah.
Great. Thanks very much, John. That was really cool.
Okay.
I definitely enjoyed that little journey. Did like the fact that you measured the performance of the breadboard versus the Vero board. It's very useful to see that.
Breadboards are terrible, really. I mean, the little jumper wires. I mean, I don't know whether I bought some little cheap jumper wires, but some of those had a resistance of about 1 ohm. And given that they're only about sort of 3 inches long, some of those little cables, 1 ohm is ridiculous, really. But I think the Chinese don't like putting too much copper in things.